It's a real pleasure for me to introduce this morning's speaker, Eric Wiener, to you. Eric is Professor of Nuclear Engineering here at the University of Illinois at the Urbana-Champaign campus, and he is also Professor of Medical Information Science at the University of Illinois' Chicago campus. He's also a member of our Beckman Institute Magnetic Resonance Imaging and Spectroscopy group. Today, Eric has kindly agreed to tell us about surfing the waves in the microcosmos using light waves to view the body. Please join me in giving Eric a warm welcome.
Well, thank you very much for coming today. I'm very excited to be able to give this talk to you.
The final frontier.
Well, not really. They've been selling that to us for decades now, that space is the last frontier to explore Earth. But actually, in the macrocosmos, we still have the oceans, and as scientists, we explore the microcosmos. Unfortunately, we can't shrink ourselves down and get inside bodies and get inside atoms, so what we do is we ride waves just like Columbus. But instead of riding ocean waves, we ride light waves. Light waves are typically anything in the electromagnetic spectrum. This includes cosmic rays, which are very high frequency, gamma rays, which are used for radiation therapy, X-rays, which are used for diagnosis, ultraviolet rays, which we sometimes burn ourselves with, visible light, most of us are familiar with, infrared we use for heat, microwaves we cook, and radio waves we all listen to. But in addition, we also can use radio waves for diagnostic imaging as well. Not quite radio waves, but energy or electromagnetic radiation in this frequency. Now, like adventurers of old, our explorations entail risks. You may recall from early physics and chemistry classes that the frequency of radiation is equal to the energy divided by Planck's constant, or the speed of light divided by lambda. I recall when I was in high school, actually, a very bad joke or mnemonic that my chemistry teacher gave me, and that was, when somebody asks you what's new, just tell them E over H. I said it was bad. Now, some examples of injured scientific explorers include Becquerel, who actually used to carry a sample of radium around in his pocket that Madame Curie had given him. This was long before they quite understood radiation, and he had severe skin burns from it. In addition, early radiologists suffered from hair loss, reddened skin, and skin lesions, and they also tried to use radium to cure arthritis, and a number of patients died from that. This was in the late 1800s, early 1900s. Biomedical researchers today can potentially expose themselves to AIDS, hepatitis B, or various unknown tumor viruses, especially when working with human tissue samples. However, the rewards of the discovery and knowledge that your discovery may help others provides a significant good feelings or makes those risks significantly worthwhile. Today, I'm essentially going to discuss two of the fastest growing applications in medical science. They include positron emission tomography, or PET, and magnetic resonance imaging, or MRI. These modalities provide modern-day explorers with a minimally invasive technique for studying biological systems. Now, particularly, the excitement about PET stems from the observation that many of the elements found in the human body have isotopes that emit positrons. In particular, these are carbon-11, nitrogen-13, and oxygen-15. These are essentially the half-lives. This is a positron emission is a form of radioactive decay. The half-life is how much a specific activity or how long it takes for a specific amount of the compound to decrease by half. And in addition, you have another isotope, which is fluorine-18, which can be substituted for hydrogen on many biologically important molecules. Its half-life is 110 minutes, and in fact, Dr. Katzenellenbogen, who's in the chemistry department, manages to label estrogen with F18, and they use this as a form of breast cancer diagnosis using PET. I have a question for you. If you wanted to study brain function, what nutrient might you substitute with fluorine-18? Any biologists? What was that? I heard somebody give a guess. How about a metabolite of glucose? One of the things that they've managed to do is to use a compound called fluorodeoxyglucose, which the brain will take up but won't use. So what happens is when your brain is active, it metabolizes the glucose and accumulates the 18 fluorine-labeled glucose. Now, oh, I can't. Do you have a laser? Yeah. Now, this is a slide that is essentially an atlas of the brain, and one of the things I want you to notice is that in this back portion of the brain, there's something called the primary visual cortex, and in slides we'll show essentially where when the brain is exposed to things like light or flashing lights, you can see fluorodeoxyglucose accumulate in this region of the brain. So what I have here then is a PET image of the active human brain. And what psychologists have done is they've used 5 different cognitive paradigms to test brain function using PET. What you see here then is what happens if those of you who are still awake are looking at this slide. This region of the brain is working. For those of you who can hear me, this section of the brain, for those of you who are thinking about what I'm saying, this section of your brain is functioning. And for those of you who will remember this talk when you leave, this section of your brain. And if you're doing all of those things and working, you can see these sections of your brain are actually functioning right now. Which one? This one? That's the primary visual cortex. And so it's hard, even one of the things that people have noticed is that even if you've closed your eyes and can imagine pictures, your visual cortex is lit up. Now this is a picture of a PET imager. They're very expensive, and in addition, you noticed how rapid those half-lives were. In order to make some of those compounds, you need a cyclotron, and there are not many hospitals with cyclotrons. But this is a picture of a clinical imager. You see a computer. You see here, essentially, a patient gantry, which they stick in after injecting you with a radionuclide. And then this system, essentially, has a series of detectors, or an array of detectors, which are simply worked by fluorescence. And these can be sodium iodide or other detectors. And essentially what happens is the gamma rays come out of the patient. They hit sodium iodide. The sodium iodide absorbs the energy and then fluoresces. And then you have a called a coincidence circuit, and that sends the information to a computer, and then your computer essentially does a series of tomography. In fact, the Nobel Prize was won by the person who developed computer-aided tomography, which works with X-rays. And he did that in '71. He won it a number of years ago. Can anyone tell me why you might get two rays coming out? Or essentially a question is, what do you think the physical principle is that generates the gamma rays for this detection? Again, Star Trek used some of this concept in its shows. The fact that energy and matter are interconverted, or as Scotty used to say, the antimatter containment field is breaking down and I can't keep it up much longer. Well, positrons happen to be the antiparticle to electrons. And when a positron comes out with a certain amount of energy, it ricochets around inside of you for about 1 millimeter to 3 millimeters with that particular path length before it collides with an electron and annihilates one another. Now, the reason why you get that particular energy is essentially brought to us by Einstein. And again, energy and matter are interconvertible, and that's what E equals mc squared essentially means, that you can convert matter into energy, and that's what happens with positron emission tomography. Since the positron and the electron are antiparticles, they have the same mass. That's 9.10 times 10 to the minus 31 kilograms. You have the speed of light. A unit of energy is called the joule. It's also an electron volt, and to convert joules to electron volts, this is the conversion factor. So if you plug these numbers in, essentially, you get 0.511 MeV, or mega electron volts. That's essentially the energy that people are looking at of the gamma rays. Or that is, each particle gives off this energy. Now, MRI also offers an ability to non-invasively monitor brain function, and this includes both brain function and metabolism. Now, before we showed with PET that you're actually monitoring the uptake of glucose. What we're doing now with MRI is you're monitoring changes in blood flow. There we go. In this case, this is the same psychological paradigm where you're flashing a light at 7.5 hertz in front of somebody who's actually got their head inside of a magnet. And what you can see then is, again, the primary visual cortex lighting up. This was done at Chicago with some of the psychologists on campus. Much like the PET machines, or I should say the MRI and PET machines look very similar. That's because doctors have a hard time dealing with things that are different. Again, you have a gantry with the system that the patient goes into. You have a computer, and much of the software is similar. It's computer-aided tomography. However, the machine is quite different. Here, you have a very large magnet that's between 1 Tesla to 1.5 Tesla and a series of gradient coils. The system that we use in the Beckman Institute, and it looks very much like the one that I have shown here, except for one difference. The hole here is 1 meter, and the hole in here is about 30 centimeters. In addition, our system is passively shielded, which means that we've put a lot of iron outside of it, and this puts the flux of the magnet back in, the flux of the field back into the magnet, so we get a little more oomph out of our superconductors than other people. What two physical principles do you think might apply to a mass and a charge that spins? Paul gave you one earlier. Yes?
One of the mechanics that the electron.
Not quite the electron spinning. Right now we're talking about mass, but you're close. Yes? That's right. And your name is? Andrew? Thank you, Andrew. Yes, the gyroscope. And what that means essentially is angular momentum. If somebody would come down here, we can demonstrate angular momentum. Want to? I don't know if any of you have seen this experiment before, if you sit down in the chair. Oh, that's not. Okay, if you take that and now turn it 90 degrees. Well, he's spinning very slowly. Now turn it 180. There it goes. So that's what happens with a spinning mass. Essentially, you have angular momentum. That's one of the basic physical properties that are involved with nuclear magnetic resonance. But instead of having a wheel spinning, you have a nucleus spinning, and the nucleus has mass. It's very small. What might you think? Okay. There we go. Thank you very much. And your name is?
Osama.
Osama? Thank you, Osama. What might you think would happen if you have a charge spinning now? Remember, you have protons and neutrons in the nucleus, so if you have a nucleus spinning, you have mass and charge. Yes? You have half of it. What goes along with an electrical field? That's right, a magnetic field. Your name is? Jim? Come on down, Jim. Chip. Sorry. Come on down, Chip. If you want to throw this switch for us, what you're observing over here then, essentially, is a compass, and what we've done is we've started a current through a coil. And you see, essentially, the magnetic field affecting the compass. Thank you, Chip. So these, then, are the two basic principles that are responsible for nuclear magnetic resonance and for magnetic resonance imaging. That is, the nucleus spins. This spin results in two fundamental physical properties, angular momentum and a magnetic moment. Now, in clinical magnetic resonance imaging, what we're primarily looking at are the hydrogen molecules on water. The body is about 70% made up of water. Hydrogen itself has 110 molar concentration in water. That is, it's a very concentrated solution to look at, whereas other elements have much lower concentrations and are much more difficult to look at. Now, this is probably the only equation that we're going to put up here. Well, not the only one, but the angular momentum and the magnetic moment are related by a physical constant that's particular to the atom or nucleus that you're looking at. And what name would you give it if you were discovering this for the first time? You have angular momentum and a magnetic moment. Can somebody come up with a name? Well, there were two names in the early days. One was the magneto-gyro ratio, gyro for gyroscope, magneto for magnetic moment, but we now use the gyromagnetic ratio. Now, what we've shown essentially in this demonstration is that if you have an object with angular momentum and you put a force on that object, the object will precess. It provides a torque, and it results from the applied force. Now, in the case of magnetic resonance imaging, the force that you're applying is the static magnetic field. That's that big magnet that the patients go in. And that force then is applied to the magnetic dipole that results from the moving current, which also caused the compass to move. So you get this precession. The precessional frequency then, essentially, is equal to the gyromagnetic ratio times the magnetic field. There's a minus sign simply because of current standards. You may also recall then that the angular frequency is equal to the frequency times 2 pi, and what this means is that the frequency is equal to omega divided by 2 pi, which is equal to the gyromagnetic ratio times the magnetic field divided by 2 pi, which is also equal to E over h. So that the energy of the system then is related to the magnetic field that you stick the system in. This is the fundamental equation of NMR. It stems from the basic physics of angular momentum and nuclear spin and the magnetic dipole that's created by the charge traversing the loop. The importance of this equation, essentially, is that the energy of your system is related to the magnetic field. So if you wanted to invent a magnetic resonance imaging, how might you do this? Yes? That is what you do. You measure that, but the strength of the field, well, it's actually the energy of the field of the particle in that field, but how do you spatially encode? Okay? If you have a tube of water, how would you code, let's say you have a If you had a tube of water here, how would you encode this, make this spot different from, say, this spot? Somebody raised their hand before. Was it you? Well, you can make the magnetic field in each position unique, right? So you have one static magnetic field, and then what you do is you put a gradient along that field, and then you've essentially spatially encoded each particle because the energy of that particle here is dependent on the magnetic field. And that's exactly what Paul Lauterbur did when he invented MRI. And that was one of the things that people said you couldn't do because classically, nuclear magnetic resonance hates magnetic field gradients. It destroys your signal. But by using this gradient to encode for space, he can actually determine exactly where a particular water molecule is. In addition, there's a fundamental breakthrough or paradigm shift in this kind of approach. And that is, in the old days, it's determined that the type of resolution you can get in optics using microscopy or X-ray computer tomography, the resolution, that is how small you can see, is dependent on the wavelength of the light that you use. Well, here we're using energy in the radio frequency bandwidth. However, you're seeing things sub-millimeters. So you're using energy that's in the meter size, but you're seeing things in the millimeter size. And so that's a fundamental paradigm shift or breakthrough. So now what I want to do is we actually have, I don't know how many of you are from the Urbana-Champaign area, but our lab has put together something called the World Wide Web, the World Wide Lab, and it's a program that allows you to run imaging instruments from a web browser. So if somebody would like to come down here, they can actually run our instrument. This is an instrument set up in the Beckman Institute, and we'll ask some questions about what's going on. We're logged on already. Okay.
Overhead while you're doing.
Okay. So, yes, I do need a volunteer. And you are? Chris. Okay. Well, Chris, what we have, essentially, is the imager that I showed you that was set up over at Beckman. And we have a number of predefined commands. The first thing that I would like you to do is to go ahead and hit reacquire. And what we're doing now is essentially we're collecting an image. What we have in there is an egg. For those of you actually, if you want to explore this further, we can look here. Two of the books that we're using that I've used are Principles of Medical Imaging and A Non-Mathematical Approach to Basic MRI. So did that reacquire then? Yes. Okay, if you want to take your mouse and move it down, we can get a better image of the picture. Okay. Now essentially then, what we're looking at, this here is the latebra. It's actually in the yolk. This is the yolk, and this is the egg white. Now, one of the things you can do with magnetic resonance imaging, which is much easier than, say, with computer-aided tomography, which uses X-rays, if you want to scan down a little bit, is you can control, essentially, how you look at the image. And if you want to, say, view, if you want to look at the image from the front, now, all we're doing now is changing how we're looking at the images, and what it means is that we're looking at a different magnetic field gradient. We've defined which axis we want to look down. Okay, go on. Move the picture down a little bit. The other thing that you can do is you can move a slice forward or backwards. What do you think we're doing when we move a slice forward or backward? If you want to move that down and say move slice position and go slice backwards. You may want to do that a couple of times. Anybody have an idea? What is the instrument actually doing? Yes? Exactly. And your name is? Thomas? Thank you, Thomas. What we're doing is we're telling the machine to look at a different frequency. And that frequency tells us where in the slice to look. If you move down a little bit. Further down. These are all predefined commands. There you go. Okay, so we actually want to move forward. And then we'll go a little bit further down. This will come up. So we've done a number of predefined commands, and what we'll do now is I'll take you through the detailed parameter list. And what we're doing here is essentially showing you how we're changing the frequency. Now, the gradient says, for example, if you have one measure of magnetic field is Gauss, another is Tesla. There are 10,000 Gauss per Tesla. So if you have a gradient that's 10 Gauss per centimeter, that essentially means for protons, it's about 0.04 hertz, 0.042 hertz per centimeter, or 0.004 hertz per millimeter. So when we essentially come down here and we tell the slice offset to move plus, say, 4 millimeters, we've essentially told it to move 0.016 hertz. And we can convert that to Gauss and Tesla, but this gets back to what Thomas, is that right? To what Thomas was saying, which is we're telling the machine essentially what frequency to look at. Okay, and then if you want to move up and then hit Submit Query. Now, one of the things that doctors have a problem with also, which is what you're witnessing here, is you have to find what you're looking for. So one thing they do is they can take multi-slices at the same time, which essentially chop the brain up, say, into about 10 slices, and then they can look at all 10 slices and determine where a tumor is, for example. What we're trying to find is where the vertebra is. Okay, I want to try entering 8. And this is a fairly new system that was set up. It's been run from Seoul, Korea, and Hawaii, and it's also been run at the National Institutes of Health by the bureaucrats at the National Institutes of Health, not the scientists, and it's a very easy interface to run. There we go, we're beginning to see it. This is right here. Again, we're beginning to catch the vertebra. If you want to come in a little bit more and go, that was, I think, +8. Mm-hmm. So if you want to try 12. Now, the field of view, which is the FOV, which is right here, determines the type of resolution. In computer tomography, you have a certain number of pixels, and in this case, we're 256 by 256, and you divide that into the 8 centimeters by 8 centimeters, and that gives you the resolution. So if you decrease the number of centimeters in your field of view, you can increase the resolution. In addition, that's very good, we're getting there. These, right here, what you see are some motion artifacts. In addition, the slice is, this is 4 millimeters thick. What, again, is you're telling the machine essentially is what the maximum and minimum wavelength or frequency to look at. And you can change that. For example, we can go to a 1 millimeter slice, actually. We can go to a 1 millimeter slice thickness. Okay. And that essentially decreases your signal. And the reason is that for MRI, remember we're looking at the water molecules, your signal intensity is a function of the number of spins or the amount of water that's in your slice. It also depends on 2 parameters which are relaxation parameters, and they have to do with when you stick, this again has to deal with quantum mechanics, but it has to do with when you excite a system, it essentially has to relax. The amount of energy you put in it has to get dissipated in some way, and the time that it takes to dissipate that is what's called a longitudinal relaxation time for one axis and a lattice, spin lattice relaxation time for another lattice. And that affects your signal intensity. And here what we've done is by decreasing the slice thickness, we've decreased the number of water molecules in the slice and therefore decreased our signal intensity. You can see that the signal to noise essentially is much worse with a 1 millimeter slice than a 10 millimeter slice. And I apologize for using an egg. I was hoping we could show some animals with tumors today, but the people who actually run this machine don't come in on Saturdays, and so we had to set it up last night, and the animals would wake up if I left them overnight. Okay, thank you very much, Chris. So essentially what I hope I've shown you then are 2 techniques for non-invasively viewing the body, essentially. You can view metabolism. Oh, I'm sorry, there's something I did forget. With NMR, I mentioned that we could do both function as well as metabolism. I showed you function in this slide. This is also function. This is right finger movement. But now what I want everyone to do is to move their right finger, their right index finger, very rapidly for a very long amount of time. My fingers don't work so well. You'll build up a slight pain in your finger. Has anyone reached that level yet? No. Okay, well, that again is from glucose metabolism. If you do it rapidly enough, you metabolize glucose into something called lactate or lactic acid. And that buildup gives you a burning sensation in your muscles. It's something that affects a runner's ability to sprint or to do long distance. In essence, it's what causes muscle fatigue. And we're able to measure that, and that's what's in this slide over here. What you're looking at are some frog gastrocnemius muscles. This is a stimulated muscle. These are two unstimulated muscles. Or actually, no, I think this is your standard. This is your stimulated muscle, and this is the I'm sorry. This is the stimulated muscle. You can see the increase in lactate in the bright field, or lactic acid, and these are two unstimulated muscles. And they're just comparing two different techniques that are this technique is being developed in our lab, and this is a standard technique that people use in medicine now, and it just shows that you get much better resolution using these techniques. But the important thing to notice is that you can indeed monitor the buildup of lactic acid. Another example is when you have a carotid artery occlusion or arteriosclerosis. Sometimes you get heart attacks, other times you get strokes. Well, one of the things that happens is that you, again, build up lactic acid, and lactic acid is supposed to be a very early measure of your ability to recover from a stroke. And so one of the things that they've done in this model, you have a gerbil brain where they've actually caused an occlusion in one of the carotid arteries. And again, you can see in the infarct brain, or the part of the brain with stroke, you can see a buildup of lactic acid, and this is the normal brain. You'd see no change in lactic acid at all. So what I hope that I've done then is essentially shown you two techniques and given you an introduction into some of how the physics of these techniques are used in everyday modern medical techniques. Thank you.